Now we've established that if we cut this piece into two pieces, this 100 centimeter piece into two pieces, and take one piece, bend it up into a rectangle or into a square with sides x, and then bend this piece up into a triangle, the area of the rectangle, of course, is x squared, and the area, well, the sides of the triangle all have length 100 minus 4x over 3. What I'm pointing to, not what I'm saying. Okay, 100 minus 4x over 3. So, what's the area of that triangle? Well, that takes a little bit of work. Of course, there's a formula for the area of the triangle, but at the level of this course, you should be able to figure out that formula and apply it to this situation. Now, the easiest way, I think, to do that, and there are various ways, at least one of the easiest ways, you first draw your equilateral triangle. And you say, okay, I don't want the sides to be a complicated expression like this when I'm trying to figure out how to find the area of an equilateral triangle. I'm just going to call the sides S, S, and S. Okay, so how do we determine the area of this triangle? Well, if we knew the altitude of the triangle, we could multiply it by the base, take half of that. So, to find the altitude of the triangle, we can simply split the triangle in half by drawing an altitude here, making right angle, and by the symmetry of the situation, you know, this triangle is equivalent to this one, congruent to the two small triangles are congruent, let's put it that way. And either of those triangles will have a side of 1/2 S, and another side S, and a side of height h, side of length h, where h is the altitude. And then the area is going to be 1/2 the base times the altitude. Now all we have to do is figure out what's the altitude in terms of s. Well, this is a right triangle. This half is 1/2 s because, of course, this altitude splits everything in half by the symmetry of the situation. So we have a side of 1/2 s, a hypotenuse of s, and a side of length h. So the legs are 1/2 s and h. The squares of the legs add up to the square of the hypotenuse. So the square of 1/2 s plus the square of h equals the square of the hypotenuse s. We usually then solve for h. First of all, h squared, subtract the 1/2 s quantity squared from both sides, and then 1/2 s is 1/4 s squared. So we have s squared minus 1/4 s squared, which is 3/4 s squared. So h squared is 3/4 s squared, so h is the square root of that. And the square root of 3/4 s squared is the square root of 3 divided by the square root of 4 divided by the square root of s squared. Now, the square root of 4 and the square root of s squared can be written more simply as 2 and s. Square root of 3 is what it is. We could approximate it, but we don't want to approximate it. It's, first of all, more compact that way. Secondly, you can see more clearly how it relates to the geometry of the situation. And third, we can approximate at any stage we want, to any degree we want, depending on the situation. Okay, so h is the square root of 3 over 2s. Therefore, the area is 1/2 the base being s, and the altitude being square root of 3 over 2s. So we have the square root of 3 over 4 times s squared. Now, of course, we're interested in finding the area of this triangle. And as we worked out here, the sides of that triangle have length 100 minus 4x over 3. So, what's the area? Well, yeah, here we go. The triangle area, I didn't remember where I'd written it. You never know where it's going to be on the board. Okay, the triangle area is what? Well, S equals 400 minus 4x over 3, so the area is square root of 3 over 4 times the quantity 100 minus 4x over 3, all squared. That's the expression for the area. The total area, which we're asked to find, the total area of the two figures, is what? Well, we have area x squared for the square, and we have this expression for the area of the triangle, so the total area is this. Now, I say that area function, x squared plus the square root of 3 over 4 times the quantity 100 minus 4x all divided by 3 quantity squared, can be put into the form. Now I was a little, I said is puttable into the form, can be put into the form, obviously. A of x equals a times the quantity x minus h squared plus k. How do we know that? Well, we know that because this is a quadratic function. Now, I asked the question in class, what kind of function is this? And the best answer I got, well, maybe it's a linear function. Well, it isn't a linear function. It's got x squared in it. But at least the answer indicated somebody's thinking in terms of different types of functions. And we haven't studied quadratic functions, although we've used the terminology. Okay? And that's coming up. So one reason I mentioned it here is just to kind of foreshadow what's coming a little bit later. Actually fairly soon, because we're finishing this chapter, and the next chapter very quickly gets into quadratic functions. Okay, so the total area, in any case, is a quadratic. If this is all expanded and everything, we're going to have an x squared term, we're going to have an x term, and we're going to have a constant term. We know then that we can complete the square. Okay, if we complete the square on that, we're going to have something times x minus something squared, or x plus something squared, but the h could be positive or negative, so x minus h could mean x plus something if h is negative, right? And this h has nothing to do with the h we coincidentally used over here, incidentally. Totally different. This is a standard notation that we use in simplifying quadratics. So long story short, we can complete the square and we will get something in this form when we do. And the advantage to that is now we can see this as a transformation of the x squared function. We transform the x squared function, we could first translate it h units in the x direction, either positive if h is positive or negative if h is negative. Then we can vertically stretch it by factor h, and then we can vertically shift it k units. So that this is nothing but what we're working on right now, translations by, transformations, vertical and horizontal shifts, vertical stretches. There are also horizontal compressions and other things, as we know. So this expression would be one of these, and this expression would reach its minimum value when x equals h. Because when x equals h, this square is 0, and the square can't be less than 0. A is positive, as you can tell from the fact that all our x squared terms are going to end up being positive. When x equals h, this term is as small as it can be. K is a constant term, so when x equals h, we've got it. We also know what the value of the area is when x equals h. That's just going to be k. Now, of course, we have to complete the square and put this thing into this form, and that's not as bad as you might think. It's a little, it gets a little messy, but it's not bad. So that's the kind of thing that we're going to look at in the near future. So it's worth thinking about that in terms of this situation. And also the fact that, if we cut the thing all the way down here, then we, in other words, we use all 100 centimeters for the square, then we're going to get a certain area, but with no triangle, okay? If we cut it up here, in other words, use all 100 centimeters for the triangle, we're going to get no square. Now, if we cut it all the way down here, our square is going to be fairly big. If we cut it all the way up here, our triangle is going to be fairly big. Analyzing this expression, putting it into this form, shows us that the maximum possible, that we get a smaller area by mixing squares and triangles than we do by either cutting the whole thing into a square or cutting the whole thing, by bending the whole thing into a square or by bending the whole thing into a triangle. This function allows us to make that interpretation. I mention all this simply so you'll understand that this stuff can mean something. Now, you're probably not going to end up bending a lot of wires into squares and triangles, but the same principles apply to business and economic models, to models in physical systems, to models in engineering systems, to models in all kinds of systems. So the kind of thinking we're doing here transfers over into systems that really have a lot of importance, a lot of meaning. We use these simple models because they're easier to grasp than the models that we have in some other fields, but they have all the aspects of those kinds of functions, those kinds of interpretations. So we need to learn to interpret these things in order to apply this kind of knowledge to the kinds of systems that will really make a difference.